We're the team working on the desktop Glovebox project. My name is Ali Al-Ghamdi, and this is my teammate, John Ha. So the project definition of our project is to design a box to perform and observe sensitive experiments. The box should include HEPA filtering for the air inside the box to help perform better observations. It should also prevent the harmful UV light from entering the box in a way that it might affect the material being observed. Our client for this project is Professor Brown here in Boston University. Here in this photo, you can see the disk space that the Glovebox is designed to work with. The box is designed to be mounted on the optical breadboard while being used, and it is used for general nanotechnology work, including observing droplets from a pipe-jet inkjet printer.
And so to give some background information about our project, Gloveboxes are sealed enclosures which allow users to manipulate materials where a separate environment is desired. And so Gloveboxes can protect the object of interest from the surrounding environment, as well as protect the users from working with hazardous materials. And our preliminary research allowed us to identify 4 major components of all Gloveboxes. And these include the viewing ports, which allow users to observe the procedures carried out in the workspace, airlock chambers, which are separate isolated interiors within the Glovebox for transferring materials, atmospheric monitoring, which provides a method of controlling the interior air and atmosphere to a desired condition, and a door typically made of the same material as the viewing port into that main workspace. And these features can vary in terms of material complexity and methodology based on the required necessities of the experiments and techniques. And so Gloveboxes are very essential tools that enhance research and development capabilities by providing a framework to carry out procedures in a safe process. And these devices are highly implemented in a diverse field of industries, from pharmaceuticals to semiconductor companies. However, a few major setbacks in modern Gloveboxes is their lack of portability. Typically, the more complex these features, the stationary they become, and this can lead to higher costs of creating, implementing, and maintaining such a device. Ultimately, this project is aimed to design a Glovebox that is appropriate for small-scale lab settings, to include only specific features as requested by our client in the project description.
So the first requirement of the Glovebox is for it to have UV light filtering. The Glovebox is being designed to perform experiment and observation on sensitive materials in the lab setting. And so protection against the harmful UV light, mainly UVA and UVB, is essential. And to make this protection possible, the transparent side of the Glovebox has to have UV light resistant to it. And the other requirement of the Glovebox is the HEPA filtering. HEPA stands for high efficiency particulate air. This type of air filter can theoretically remove at least 99.7% of dust, pollen, mold, and other airborne particles with the size of 0.3 micron. The Glovebox is designed. The Glovebox design is required for it to have HEPA filtering system that creates a positive pressure to protect the inside of the box from the harmful particles outside of the box. And different HEPA filtering have different efficiency relating to the size of the particles being captured. MERVs, or minimum efficiency reporting values, is used to measure this efficiency. And our HEPA filter has the rating of 12 out of 16. Here you can see a figure that shows the design of the Glovebox. The middle of the box is where the working space is located. It is surrounded by 5 opaque sides that act as the walls of the box, with the bottom side being empty. The front side also acts as a sliding door to provide access to the working space, and the top side contains the HEPA filtering system. The box is designed to be safe to use, have low operating and maintenance costs, and be easy to set up and move around. The design process can be categorized into 4 different phases. Each of the first 3 phases focusing on one of the major components of the Glovebox, and the final phase was for the final adjustments and modifications. And now we'll go through each phase in more detail. Phase 1 of the Glovebox design process was focused on selecting the optimal way to provide UV light protection for the box. At first, we chose to apply UV filtering, clear polyester sheets into transparent acrylic sheets, and for that to make up the sides of the box. What you can see in these photos is the feasibility test we demonstrated to measure the effect of the UV filtering sheets. We used a UV flashlight to test the effect on a type of resin that hardened when being exposed to UV light. And here, you can see the results. which prove the effectiveness of UV light resistant sheets.
And so in phase 2 of our design process, we designed and created the main frame assembly for the glove box. We began with an initial idea of using aluminum T-slot frames as the frame members for the device because they're known for their strengths, and a special feature with the rail extrusion. This rail extrusion runs along the length of the T-slot and can accommodate the inclusion of panels and sheets, so as long as those the thickness of those panels are equal to the widths of the rails. And this material especially matched with what we were looking for because we needed to design a way to include the UV acrylic sheets as viewing sides or the viewing walls of the device. And so figure 1 here shows an example of how a clear panel can easily slide fit into the rails of the T-slots. And so with the correct dimensions of the panels and T-slots, we can essentially assemble 4 of these parts to form a cubical frame assembly with the UV acrylic sheets as the walls of the cubes. And then so we see in figure 2 what this should physically look like. This figure is our initial 3D model prototype. As mentioned before, this box is composed of T-slot frames with the acrylic sheets as the viewing walls. A satchel door was designed and located on the front side of the box, and the blue prism on top of the model is just a placeholder for the HEPA filter system that was not designed at that time. And after some review and feedback with our client, 2 major changes had to be made to this initial design. So namely, the first is the satchel door had to be replaced with a sliding door in which one side of the cube can entirely be vertically lifted. And this was to accommodate more space and access into the workspace when working with various size materials. And the second thing that we changed was the HEPA filter system. Our client did suggest that the system did not need to encompass the entire area of the top panel and rather can be a little bit more compact. And so figure 3 here reflects the changes that were made from the initial design, where we replaced that access door and designed a smaller filter system. And while this was a step closer towards our final design objective, the model did not truly reflect the accurate dimension of the glove box. And additionally, some redesigning of the mechanism and the filter design had to be reconsidered. Oh, and so after another step of revision, figures 3, 4, and 5 show the most up and final CAD model of the glove box. This design contains accurate dimensions and incorporates the major changes that we mentioned previously. Additional things to note with this model is the inclusion of a track mechanism for the door and a fully designed HEPA filter system. And so we proceeded to create the physical prototype of the glove box, hoping that this final product would resemble the work we've been doing with our virtual models. And the images shown here are materials which were delivered to us. These include the T-slot frames and the connectors. The third and fourth you can see is when we first initially assembled the main frames together. And as you can see, the progress of the glove box from virtual model to a physical device. The only parts missing here are the UV acrylic sheets and the filter system. And so phase 3 here focused on designing the HEPA filter system. Now, initially, we believe this portion of the project to be one of the most challenging because of our just general lack of expertise with electronics and the fact that this part is a little bit more technical than the rest. However, with assistance and guidance from our advisor and client, we began the design of the filter system by approaching or examining a simple cooling fan. And we found that a typical 120 millimeter cooling fan consists of red and black wires that can be stripped and connected in series with red and black wires of other multiple fans to create a much larger and powerful fan system. And ideally, this was our filter system's essential mechanism of allowing that filtered air through the interior of the glove box. So we decided to have a system of 6 cooling fans linked together to blow in this filtered air at the same rate. And the circuit implementation is shown in the figure on the left. Oh, go back.
Okay.
Yeah. So with the use of screw terminal blocks, it's the image shown on the right. One block can be dedicated to all 6 red wires, while the other terminal block can be dedicated to all of the 6 black wires. So the stripped wires of the fans can then just simply be inserted into the port, secured with the terminal screws. And the barrier strips, these are the fork-shaped strips in the image, they're connected to the other half of the terminal block as a method of linking the respective red and black wires in series. So overall, we created this organized circuitry for the fan system with an additional connection made at the end to an inline switch and a power supply. So the image on the left shows the physical design of the fan system with the organized and secured wires to the terminal blocks. And so the fan system was then attached to the plates. It's the black plate you see on the image to hold in the individual fans. And then this ventilation plate was integrated on the top UV acrylic panel through secured screw connections. To finally complete the entire filter system, the HEPA filter is attached on top of that ventilation plate. And so through this method of positive pressure airflow, the HEPA filter, which is located on the exterior of the glove box, captures in the air particles and allows for the passing of the filtered air into the interior using our fan system. And the exact details and depiction of what I'm talking about will be shown in the next few slides. But overall, we did feel that this was a way to design. And one of the biggest advantage is that minimal maintenance is required because of the secured wire connections. And the HEPA filter only needs to be replaced about once a year.
So in phase 4, the focus was to make the needed adjustments and modifications on the glove box. We substituted the corner connectors we chose initially with 3-way corner connectors because it was cheaper and easier to assemble. We also changed the door access from an opening door that was cut into the front side, into the entire front side being a sliding door. And this was done to provide more space when accessing the inside of the box. We also positioned the fans alongside the ventilation plate to create a better air filtering system, and also changed the wiring connection of the filtering system to make it more safe and easier to operate. And finally, we replaced some of the mechanical fasteners and screws to create a more seamless, sturdy assembly. Here in the results, you can see the final product we had and different views. And this is the video.
Yeah. So here we'll show you a video demonstration of the product. So once the device is connected to the power supply, the user simply toggles the switch on for the filter system to start. And the HEPA filter you see can be removed, and underneath you see the fan systems operating with the same rated RPM. And so some of the positive evaluations of our design is that it's a very strong structure with the T-slot frame members. Very minimal space gaps exist, which provides that framework of an isolated environment. And all is controlled with a full operational filter system. And overall, it is quite an efficient and ergonomic design because of its simplicity and requires really minimal user interaction to activate and use the features of Glovebox. And so the total cost of producing this shown here. The table lists all the materials, quantities, and their respective costs, contributing to our total expense. Now, the budget for the Capstone projects were aimed to be a certain amount. However, for our project group, this cost constraint was not able to be realized because of the high cost components required for the specific feature of our device. So in particular, see that the top 2 most expensive parts of our product were the UV acrylic sheets and the T-slot frames, which is practically speaking our product in its entirety. So with approval from Professor Hauser, we were able to still move forward and continue with the project, sort of overlooking the given budget, however, while doing our best to reduce the cost and stay within reasonable cost limits.
So our journey while researching, designing, and constructing the Glovebox were met with various challenges. During the early stage of the process of designing the Glovebox, many of our efforts were focused on creating a virtual model of the Glovebox. The purpose of this was to provide a way for us to visualize the product we have in mind and help us better select the different parts that will come together to create the Glovebox. Having limited experience with 3D modeling and with the different complex shaped parts that we selected for the Glovebox, creating a virtual model proved to be quite challenging at times. The other challenge we faced was assembling the Glovebox once all the parts were purchased and arrived safely. The Glovebox contains many complex parts, and assembling them together was quite tricky. We also had cost constraint to deal with. So when we first selected the different parts we wanted for the Glovebox, the total cost was way over budget, and we had to research replacement parts to stay within reasonable budget. Another challenge we faced is that we both were working remotely from the university and from each other. This made finding the suitable working space and tools more challenging, and we had to ship parts back and forth between our 2 locations to work on the project.
So even though the Capstone project concludes today, we do think it's in our best interest to follow up with our client in the next few days, receiving any feedbacks as well as addressing any other further necessities. And if we were given an opportunity for another year to work on this project, we would definitely design the glove box for further improvement in features. Some ideas to throw out are to include digital components, such as like fan speed modulation or user interfaces for the filter system. We would also look into more substitutions of the materials and components to reduce the overall cost while maintaining the essential features of our device. And so but at the end of it all, the Capstone project was an extremely tremendous learning and improving experience for both Ollie and I.
We finally would like to acknowledge Professor Brown, the client for our project, and Professor William Hatter, the advisor.
Yes, and a special full extended appreciation to Joe Estano from Epic, along with Myung-Soon Choi from 3J, who have both tremendously helped us with the machining, assembly, and modifications of our product.
Thank you, and we're open to any questions.
Okay, good job, guys. I had a one question about how did you figure out the size of the compartment that goes on the top? You know, the number of fans that you needed, and did you? It doesn't sound like you were able to test it enough to be able to know was that the right? In fact, was that the right fan amount and the flow rate into and out of the chamber? But did you do some calculations to figure out what kind of flow rate and therefore the fan size you need, so to be able to figure out the size of that compartment?
Well, so first of all, the size of the compartment was based on the ventilator plates. The dimensions are shown when we purchased the product. And so one ventilation plate holds 3 CPU fans. And so the reason why we chose 6 was because initially we just tested 2 CPU fans, noticed that the airflow wasn't as strong. So I guess this was kind of an approximate that 6 would be good enough. So we did order 6 fans. Unfortunately, we did not do any procedural experiments or any mathematical calculations to determine the most optimal flow rate of our device. It was basically mostly through just prototyping and designing.
Okay. Well, thank you.